Now, I first met Todd a number of years ago at a DARPA workshop on advanced prosthetic limbs. I actually went to that workshop expecting to rub shoulders with famous roboticists and neuroscientists, and I did, but it turned out it was a fellow Chicagoan who really stole the show that day. Unbeknownst to me, I didn't even know the man. He had been developing a nerve transfer technique that he called targeted muscle reinnervation. At that workshop, he showed us a video of an amputee using his prosthetic limb in the most coordinated and graceful way that I think any of us had ever seen. And not just 1 degree of freedom, but two, a gripper and an elbow coordinated beautifully. It turns out that was really the start of something big. In the years since, Todd's Center for Bionic Medicine, just up the road here at the Rehabilitation Institute of Chicago, has become the nation's and possibly the world's largest prosthetics and orthotics research center. We have 4 labs and over 40 research staff. And Todd's interests have expanded. He continues to develop targeted muscle reinnervation, but he also works on the development of control algorithms for advanced artificial legs and the development of artificial arms that are actually quite lightweight as well. And he's accumulated a list of recognitions and awards that's too long to talk about. But here's the key thing. Throughout all of this, Todd has remained a practicing clinician, working directly with patients, and by all accounts, one of Chicago's absolute finest. He's indeed a rare example of someone who can combine groundbreaking research, keeping his eyes on the things that are really important. So I ask you to join me in welcoming Dr. Todd Kuiken.
Well, thank you, Ed, for that gracious introduction, and thank you all for having me and getting up at this early hour to come down and listen to me. So what I want to talk to you today is about how can we control an artificial limb. We build different types of robotic limbs, and our mission is clear. Losing an arm or a leg causes a very severe disability. With just one limb, far less two, it actually causes an emotional disability that's sometimes even greater than the physical disability. So we have 2 types of prostheses we use these days. One is called a body-powered prosthesis, and here you basically take a strap up to your shoulders. When you scrunch your shoulders like this, you pull on a bicycle cable, and that pulls on your hook. And here you see my patient wearing a device quite similar to the patent from 1912. These are light, robust, and still quite effective, but you must admit primitive, and they're limited to body powering only 1 degree of freedom at the time. The second way of doing this is using myoelectric control. So every time you clamp down on a muscle, some electricity is released. It's actually a byproduct, and it's a very complex signal that we can use to control an artificial limb. We can use it in a simple mode, such as this, where we just take the amplitude of the flexors or the amplitude of the extenders, and whichever one's bigger, that's what we do, open or close the hand. But that is a very rough control, sure to say. So we have a number of prosthetic devices. There's 3 different arms on the market. There's a plethora of new hands coming out, but how do we tell them what to do? We need a neural interface. One place you might think about is going straight to the brain, and there's been a lot of exciting media about doing cortical recording in humans. However, that's really, really hard, and to date, they've not been able to get the cortical recordings lasting more than months to a couple of years. Furthermore, this has been with spinal cord injured patients and not amputees who run around and play football. Another exciting place to do it would be straight from the nerve. I can tap the nerve of a World War II veteran, and he or she will still feel their missing arm. So the nerve stays alive, and the potential of recording directly from that nerve, or the data trunk, if you would, is very compelling. But again, it is very, very hard to do. The signals are in the order of microvolts. They're embedded in background EMG noise that's 3 orders of magnitude higher. And you have to have very fine electrodes in that array that have to survive what we call the flying kid test. Before fatherhood, I never imagined about how many places I could get bruises, and you can imagine having this delicate little array in your nerve and your son going, "Hi, Dad." and ruining it. So it's some exciting work, but it's been taken a long time to be able to come to a clinical value. So I wanted to do something that was more immediate and simpler. And we thought up the idea off of the end of, actually I was reading a paper and there's a one-liner at the very end. Someone suggested, well, why don't you move the nerves to the muscles and let the muscles be your biological amplifiers? And that intrigued me, and thus really began my research career. So what we now do is a technique called targeted muscle reinnervation. You have 4 main nerves that come off of your arm, and unfortunately, they're kind of bundled into separate functions. And we can move these 4 nerves anywhere we want as long as it's to healthy muscle. So imagine someone who's lost their arm at the shoulder. We can put those 4 nerves on different segments of the pectoralis major, minor, and even other muscles. And then, when you think close hand, that's primarily a median nerve function, it will make this piece of muscle contract, and we use the signal from that to say hand close. So you would have intuitive control, and you should be able to get at least 2 degrees of freedom of control because you have 2 signals for an elbow and 2 signals for a hand. So that was our goal, and it was very exciting. So the advantages are we are using biological amplifiers, i.e. muscle, that will last forever as long as you continue to eat your Wheaties. They'll give you simultaneous control. They'll be able to control at least an elbow and a hand. It doesn't require any implanted hardware, and you can still use that shoulder for other degrees of freedom control if you want. Furthermore, we could use existing myoelectric prosthesis technology. Now, it does require surgery, but at least on the transhumeral level, the surgery is straightforward, and on the shoulder disarticulation level, it can go well, and our results, as you'll see in a while, have been excellent. So this was our first patient, just a remarkable man named Jesse Sullivan. Jesse was a high-powered lineman, lost both of his arms in a burn, and he needed a revision surgery because these little split-thickness skin grafts were painful. Even taking a shower hurt. And here you see Jesse with, he came to Chicago because we're a center of excellence in amputee, and here you see him with that body-powered device on one side and the motorized on the other. And these are chin switches, and so he would pick which joint, elbow, wrist, or hand, he wanted to move with those chin switches, and then use that body-powered cable. And I tell you, he got really good at it, but if he was working hard, he'd also be sweating bullets. On this side, he had kind of a bony shoulder, and he was pressing little buttons to operate this elbow, this wrist, and this terminal device, or powered hook. And so since Jesse needed to have that surgery, he was kind enough to let us rewire him. I'm a rehab doctor. They will not let me operate on anything but critters. So my friend Gregory DeMania did the surgery. He's a wonderful plastic and hand surgeon. And this is the paradigm. We took the pec major. It has 3 separate divisions, so we separated them to prevent the nerves from crossing over. We moved the pec minor out from underneath, so we had our 4 targets right on the front of Jesse's chest. And again, remember, we're trying to go from 1 signal on the chest to 4 arm signals. And this is what it looked like. It was very exciting when it worked. And here you can see Jesse trying to open and close his hand and move his elbow up and down. And this is where we put the electrodes. And again, these electrodes are only going to be operating on the magnitude of the EMG. And it works. They're tough fits because you have things like crosstalk you have to deal with, but it works. And here's Jesse. On the left, he'd been using his conventional arm for about 2 years. On the right, this is 2 months after we fitted him with his TMR arm. Now, actually, we could only use 3 signals at the time because he had this very annoying interference signal on his bottom electrode. His heart. The EKG was bigger than the EMG, and he wouldn't let me stop his heart. So we had to figure out a way of filtering it out later on. And he's about 3 times as fast in this little test, and when we were able to get that 4th electrode working, I think he got as high as 6 times as fast. We also had a surprise in that after a number of months, when you touch Jesse on his chest, he feels his missing hand. And it makes sense. We put his median nerve over here, and that's where your thumb and first finger are mostly. We put his pinky on the lateral side of his wall, right where you see this sensation. Down here, back of the hand, radial nerve, and just a little bit of muscocutaneous up there. And Jesse had very high fidelity sensation. He described it as if he felt pressure only wearing a thick glove. And here you can see he had down to 1 gram of force in threshold detection with this reinnervated muscle. Many of the places he could feel just his hand. Some places he could feel his chest or his hand and attend to either. And he felt hot and cold in his hand. He could feel vibration. He could feel graded pressure. And it was very exciting because this gives us a potential to give sensation back to a prosthesis. Imagine a sensor down here telling you how hard you're squeezing your cup of coffee or your child's hand, and then feeding it up to push on that hand so you feel it and know how hard you're squeezing. Watch close. This is another patient with sensation. We call it targeted sensory reinnervation on her chest. This time we did it on purpose. And she could feel different grits of sandpaper and ribbon cable. And she said when she rubbed that sensor, which I believe Ed's group made, back and forth, it felt like her finger was rocking. So it's a very exciting tool to close the loop. And I must say my former postdoc, Paul Marasco, is taking the lead on it in Case Western right now. So our initial target were transhumeral amputees because they're much, much more common. And the way you control a motorized arm for an above elbow amputee right now is all you got is the biceps and the triceps. You got 2 signals, and it makes sense for your elbow because you contract your biceps and your elbow comes up, contract your triceps, your elbow goes down. But then you have to switch by co-contracting, and now you're in wrist mode. Then you got to switch again to get into hand mode, and now you're using your biceps to close your hand and your triceps to open your hand. And if you want to get back to that wrist, you got to do a lot more of that co-contraction. And so this serial, very slow control is cumbersome and quite frankly worthless. And I had never fit an amputee with a body-powered, a motorized arm at that level of amputation because the control was too bad. All right, oops, that's not what we want. So with TMR, what we do is we just leave one head of the biceps and the triceps alone, and then we take one head and put the hand closing nerve, the median nerve there. On one head of the triceps, we put the hand opening or the distal radial nerve there. And if they have a long enough arm, we can put the ulnar nerve there, which is intimately involved in both hand opening and closing. So we can get 4 from potentially 5 sites. And here we've also learned to, at first we were just throwing away, we were cutting away the subcutaneous fat so the muscle got close to the top and would give us the biggest signals. Then we learned, well, heck, let's use it, and we take it and turn it into a fat pedicle and stuff it down between the 2 muscles to give us more physical separation between our signals. And here you can see Chris, one of our first transhumeral TMR patients. Here he's using a normal device that he'd had for about 8 months, and it looks goofy, but that's actually a good way to use your hand and picking up blocks and moving them over this little wall to drop them on the other side. And you know, Chris is a lot faster. I think he's 4 to 6 times faster in this simple little task. And I apologize for showing you these simple little trite tasks, but the quantifying how good an arm works is challenging, and these are at least visually understandable. And Chris is having some fun while he does it too. All right, so, well, let's see a surprise. What's this? The same one. Sorry, I'm a little challenged here this morning. So this was my goal, and it worked. We have found that because we're using healthy nerve and healthy muscle, 94% of the time, the nerves reinnervate the muscle well. The only 2 that haven't worked is one when we found that the nerve was dead, and another when we killed the muscle by transferring it and interrupting its vascular supply. Our outcome metrics have been very strong, and the patients love it because they get more intuitive control and can control 2 degrees of freedom. This is a little old. We have well over 100 patients worldwide, probably closer to 200, but I don't have a gizmo to track, so I have to wait for the surgeons or the prosthetists to tell me, and nobody tells me anything. So I'm just guessing. We have over 24 wounded warriors at Walter Reed and now SAMC in San Antonio, as well as a number of patients in Canada and in Austria. And it works. That's the most exciting part. Here you see Claudia. She's using her arm that she named Bonus. She's got her marine pocket literally mounted into the frame of her prosthesis, which did not make her mother very happy, but she's very proud. She likes to use it for cooking and doing laundry, and when she first got it, she wore it all the time. But like most prostheses, they're heavy, they're hot, and they have limited function. So Claudia now wears it when she has a task because she's more comfortable with her body, and she doesn't need it, she doesn't wear it. So those were just simple on and off or commands that I was using, but these targeted reinnervation muscles have tons of data. In fact, they have all the data from all the muscles in the arm and even the hand. So we thought, can't we do better than this? And I met some very smart people who do math much better than I. Kevin Engelhart, one of the leaders in signal processing, and Ping Zhao was my postdoc, and we did these experiments at Jules Labs where we just saturated 5 of our patients with 100 electrodes, and here you can see what the intensity is like when you try to adduct the thumb, abduct the thumb, or supinate. But it's not like I can go, okay, I'm going to put your thumb electrode there. You get a complex pattern of activity, but not discrete points. So we did an experiment where we had them try 16 plus things, and we were amazed using a simple LDA, linear discriminant analysis algorithm, that we could average 96% of accuracy in recognizing what the person was trying to do offline. And so that even down to the point of using single digits. So that was very exciting. And of course, that was a very dense 100 electrode array. We found we didn't need 100 electrodes. We could actually get down to somewhere between 4 and 8 and do pretty well. So here I'd like to show you some really cool robots that were being used as part of that DARPA program Ed was telling you about. This is Jesse, and he's wearing an arm with a powered shoulder, powered elbow, 2 degree of freedom wrist, and a hand that can make different hand grasp patterns. And the way he chooses what hand to do is he opens it wide, thinks, do I want to be in a fine pinch, a power grasp, or perhaps a key grip? And then it'll go into that grasp and stay there until he opens his hand wide again. And Amanda is working very well using mostly a fine pinch to move those blocks around with good accuracy. And this is pretty old now. This is like 2008-ish, I think. 2007. So it was a very exciting time, but these arms were made. We only got them for 2 weeks at a time, and then they took them away. So that was disappointing. So we decided we wanted to build our own total electronic system. I mean, we've been using all this stuff on a computer. We wanted to port it to a microcontroller and use it to control anybody's arm. So here's our microcontroller. We're very proud of it, although it's hard to get too excited about any microcontroller these days. This is our analog front end with 8 channels of EMG with all kinds of programming options for gains and filtering. Then it puts it to A to D and puts it down on a CAN bus to feed into this. And this is what it's turned into. It is now a commercial product. I do have a disclaimer. I am a shareholder in this company. I have not yet made enough money to buy a cup of coffee, but I hope to someday. And it's exciting because we can now use this thin little system and fit it to any prosthesis of any kind, including some with those fancy multifunction hands. The first patient was fit last November, and we're up to about 30 fittings to date, so it's really exciting. So here is a patient using pattern recognition control. And the way it works is the arm moves through all of its motions after you turn it on, and the patient, Glenn, in this case, is following those motions dynamically. He's trying to bend his elbow, trying to close his hand, and after doing this for about 1 minute, We've collected all the data we need. It turns out the algorithm to recognize his signals, and then he's rocking and rolling. Glenn was one of our wounded warriors and lost his arm in Afghanistan and has been not just a research subject, but a great research partner, giving us lots of feedback and help along the way. I asked him one time, how does this latest arm work? And he goes, well, I give it a 7. I'm like, okay, what's that mean? He goes, well, my first arm, you know, the conventional one, that was a 1 or 2. At least it hung on my arm. It was something. And I like the TMR arm, the direct control, other kind, but, you know, it was a little tough. I gave it a 3, maybe a 4, and this one's a 7, except it kept falling off. So obviously we had something to work on in suspension. We've also gone on to do this with radial amputees below the elbow. And here you see a very good subject who is using a prosthesis we call Lumpy. As you can see, it's got little boxes glued all over it. And he can do very well. But what's interesting is our transradial amputees do great with wrist motion. And they can open and close a hand. But if you ask them to try to control different hand grasp patterns, such as those higher level TMR patients, they aren't as good. So this below elbow amputee, even though he has all these hand muscles in his forearm, is not as good as a guy who's lost his arm above the elbow or at the shoulder and has TMR. Well, we think the difference is these transradial amputees do not have any information about the hand intrinsic muscles. And if you actually get nerve damage to one of these two nerves that go into your hand, you have a very impaired hand. You end up with ulnar nerve, and you know it turns into what we call the ulnar claw. And if you lose your median nerve, your thumb function is very poor, and it is a much less functional hand. So you might guess what my next grant is. It's to do TMR in these transradial amputees, and that will be starting this fall. So there are a bunch of arms, but we are frustrated by them in that they're all made for the 50th percentile male. That means they're too big for about 75% of the people in the world. And they're heavy. Those are the things my patients complain about. They're heavy, it's kind of big, and they also complain they break down a lot. So we got tired of driving somebody else's car, and we decided to make our own car, our own prosthesis with some unique metrics. And this project really has been the brainchild of John Sensinger, one of the most brilliant engineers I know. He's now up at University of New Brunswick in Canada, as we lost him last year, but still a good collaborator. So our goal is to fit the 25th percentile female. And here you see Reva, one of my grad students who is 25th percentile female in many dimensions, and an average sized guy, Blair. And if you do that, you'll now fit 87% of adults, and you fit the average 12-year-old child. So we now have something to help at least older children, because we have no devices that are any good at this point. And we want it to be lightweight, at least a pound lighter than those other devices you saw, and that's including a 2 degree of freedom wrist. And we're on target to hit this number, bringing it down to 3 pounds instead of 4.5. We really want a good cosmesis, and we're doing that with some wraparound fingers that are spread a little bit and have a better ergonomical orientation. The contour of the wrist, even though we only have 2 degrees of freedom, flexion and rotation, they aren't perfectly orthogonal, because it turns out if you put them a little off axis, you get what's called a dart thrower's angle, and it's a much more commonly used combination in nature and facilitates function of the wrist. And we're trying to meet the benchmarks of speed and force, etc., torque, as we can compared to those other larger devices. And I promise you it's a very, very smart device based on our last 10 to 20 years of software development. So this is the hand, and I'm very excited about it. These fingers wrap around. We call it minimally actuated because it only has one motor for all of the fingers. Then it has a lot of compliance built in, and has one motor for the thumb, so it can do about 2 or 3 different grasps. It doesn't have individual finger control like some of the prostheses do. But this design, we believe, will be much more robust because the fancy hands are breaking down every few months, and we think this one will last longer. And it is also very light and very small. Oops, back up a little bit. There is a 2-degree of freedom wrist. One of the units fits kind of at the base of the hand, and here's the rotator. They have exactly the same motor and transmission with some very creative elements that John designed, including a microcycloid transmission that has very high efficiencies, very lightweight and thin. And John designed his own external motors that have about 10 times the power of other motors that we've been using by moving, those neodymium magnets to the outside and getting more torque out of it and good speed. And if you want to understand this graph right here, go talk to Ed Colgate, because I have no clue. So that's been exciting, and our arm is actually now undergoing clinical trials. We generally, when we get a new prosthetic device, we say, okay, let's see how long it lasts. And these fancy hands, they last for a few minutes to a few hours at first, and they get better, and they last a few days or a few weeks. But so far, none of them last more than a few months. Our clinical trial of that arm, we had one hand failure in the first month, and that was it. So maybe he was an easy user, but he was using it at least an average of 4 hours a day. So we're quite excited, and we plan to trial it on 10 different patients using the pattern recognition control. Well, only about 10% of amputees are arms. Okay, at least 10% of the amputations performed every year are for arms. 90% are for legs, and mostly vascular disease. So we're very motivated to work and study lower limb prostheses as well. I do want to let you know that number's a bit skewed because most of our vascular amputees are elderly and do not live as long and have a very different type of device they need, whereas our younger traumatic amputees don't happen as often, but they'll live for 50 years. So the prevalence is about equal between traumatic and dysvascular amputees. So what about legs? We have a lot of legs out there, but they're all passive devices. They might be smart to have a computer to control the compliance, to allow the knee to lock in certain positions and help people walk better. And there is one motorized knee on the market, but it's heavy. It weighs 7 pounds. And while I'm excited to help, high-level athletes and wounded warriors, I'm just excited for my elderly amputees where the hard thing is getting up off the toilet. Try doing that with just one leg. It's hard. Or going up and down a few stairs just so they can stay at home. So we're motivated to build a good control system for these types of patients. The lead on this project is Levi Hargrove. He's run it from the very beginning, initially as a 5-site collaboration. And here you see a patient who's had TMR. He had a golf ball-sized neuroma that was very painful. So when we cut it out, we took the 2 nerves to his lower leg and put them to his quadricep muscles. And here you can see, using pattern recognition, he can control dorsiflexion, plantar flexion, inversion, eversion, and of course his knee. So he has very good control of this 3-degree of movement ankle and knee. And he's this black line compared to patients that don't have any kind of TMR. But what surprises us is even without TMR, there's enough synergy that most patients do very well at controlling their knee and dorsiflexion, plantar flexion in their ankle. And so here you see if you're only worried about dorsiflexion, plantar flexion, we're in good shape and maybe you don't need this surgery. And it surprised us that there would be that much synergy to that good of control. So here you can see the devices we're working with. Vanderbilt is building a fully powered knee and ankle system with Michael Goldfarb in the lead, and Hugh Hare at MIT is actually commercialized his powered ankle system called the IWalk. And so here's a video showing you kind of where we are to date. This is Glenn. He is a knee dysartic, and he does have TMR. This prosthesis has boatload of sensors on it, plus EMG. Now, the sensors can make your mode work well, but it doesn't know when you want to change mode. So how do you tell your leg when you want to go up or down stairs or when you want to sit down? And that's where the EMG becomes very, very important. Also, when you're non-weight bearing, he can use just the EMG to bend the knee and ankle, which is useful, for example, getting ready to go from a sit to stand, or kicking your legs out and relaxing. Or what about trying to get into a small car with that tight transfer where guys normally have to pick up their leg by the pant and fold it to get into their car? Glenn does not have to do that. He can think about it, and his knee and ankle will bend. I'm going to play that one more time to highlight what's going on here. So this prosthesis has an intrinsic impedance controller that really is a state machine and works on the millisecond level to keep it stable and working right. And it's got a bunch of impedance parameters that allow it to do different types of terrain, such as the ramps or the stairs or on level. And the key issue is pulling in this EMG to know when you want to make those transitions and to do it seamlessly, which you see Glenn's able to do. And here, with a motorized leg, when he goes from a sit to stand, he can do it quite easily because that leg's matching the power, or almost matching the power, of the other leg. Now, the challenge is the devices are still too big and too heavy. That weighs almost 12 pounds. And so we need to make them lighter and, of course, robust before they're going to make a significant difference on our patients. So last but not least, here, just so you know that all the patients aren't in Chicago, this is a case that was done in Canada. He has TMR. He's what we call direct control, none of the pattern rec yet. He's got great range of motion and really good control. And I've been blessed with great funding from the NIH, the Army, the DARPA, NIDER, and philanthropical support to make this all happen over the last 30 years. So thank you very much, and I'll be happy to take any questions.
Thanks, Todd, for a terrific talk. We do have time for questions, so please, microphones right up here at either side. Don't be shy.
Sir, there's a microphone right there.
Thank you very much. It is very fantastic talk. You have pointed out several times that the robotic prosthesis is too heavy and too big. So I'd like to ask you to share some idea or opinion, what providing us robotics community some direction, you know, how to make it light, and what is their direction to push our research direction to make it heavy and make it light.
Well, the first thing to do if you want to go into rehab engineering is you really have to understand your patient population and what the critical issues are. I think, for example, the legs we're making are very heavy because they're meant to do everything. They're meant to walk, they're meant to be able to even run, do stairs, whatever, with a lot of power. And the question is, do you need all those things for all patients? So if you can understand your patient well and understand what's important to them, sometimes you can trim down the list. From there, it's very important that you interact with the patient from the very start as you look at designs and your clinicians who integrate patients' input to, again, figure out what's important. But I will challenge you as the robotics community, you guys make great, big, fancy robots, but the lightweight, articulate devices are still lacking. We have 1, 2, 3 different prostheses out where they put a motor in every finger, at least one, if not two, in the thumb, and they're capable of doing lots, but they break down all the time, and it's not useful if you have to send your hand off to Scotland or Germany or someplace else to get it fixed. It's annoying, and it needs to do better than last for only months. So the good clinical collaboration and very strong engineering is what I believe it takes, and obviously I'm prejudiced because that's the kind of team I've tried to build. I don't think they've had their coffee this morning, Ed.
That looks like we've got a taker.
Please.
Yes, this is very exciting and really groundbreaking work. I was wondering if there are any ethical issues involved, and what are your thoughts about this?
There's always ethical issues whenever you're dealing with a patient. Surprisingly, I don't have to get any special permission to do any kind of surgery I want, as long as I'm not publishing it. So surgery can be relatively unregulated as long as it's thought that it'll be good for the patient. We did do an IRB, and we're very clear and explicit on what that was so that we informed our patients of the risks and benefits very well. The benefits were clear. The risks were that the nerve might become painful, although that has only happened once that I know about of like almost 200 patients. And at first, I was also very careful to take the best kind of patients, a patient who I could trust, a patient who was going to be compliant, and I got to tell you, people like Jesse and Claudia and Amanda were a few of my first, and they were wonderful patients and true research partners. So you have to be careful, and I put them all through psychological testing. I had everybody on the team meet, and we looked for what we might worry about and what the baggage was, because there are no perfect patients. There are no perfect people. We all have our baggage, and the question is, what is the baggage, and will it interfere with what needs to be done, and is it safe for this person? One last point is, I've had many, many media requests to follow a patient from beginning to end, and I will not allow that. I think it puts too much pressure on the patient and the team, and that pressure is just unnecessary and unwarranted. So I'll be happy to show off, the result of our patients to the media, and we've done so many times, but I will not let media follow the process because it's just too much pressure. And to be honest, it takes way too much of our time with all those cameras. Yes, sir.
You are showing one device at a time, either an arm or a leg. Have you done any work on both devices at the same time?
Both the arm and the leg?
Right. Or two arms?
We do have a bilateral amputee. If it was my own computer, I'd show you. He had TMR on his left side at the shoulder, and this man had so much surgery because he was a burn victim. His scapula was a mess, full of bony stuff that we had to chip off for hours. And then on the right side, in a separate surgery, he had a nice long arm, but he also had burned off his biceps. So the surgeon took the brachialis muscle from his leg, which has anterior and posterior motor points, put it on his arm to make him a biceps, did the targeted reinnervation, and covered it with split thickness skin graft. And I'm really sorry, I meant to include that video today, but unfortunately I didn't, and it's an awesome one. I'm going to just look to see if I have it. So that was our first case of bilateral, and that was last November. And I did not include it in my thing, and it's not my computer, so I apologize.
Another question?
First of all, thank you very much for the interesting talk.
Thank you.
There's a movie that led me to the robotics world, is the Terminator 2. And I'm glad to see maybe one day such thing is happening and it's helping people who really need it. I know a lot of things.
Yes, my patients are much nicer than Terminator 2. And to the best of my knowledge, they have not killed anyone since. Although there have been some children that has been threatened to be beat to death with an arm.
Yeah, So I know a lot of things that decide how we grasp stuff is based on what we perceive. And I know EMG is playing a very important role in controlling the arm. But there's other research focusing on like using EEG signal, try to understand how people want to control that instead of using the muscle signal. So can you please comment on that and probably give us a little bit idea about the difference between these two types of research, in your opinion?
Well, you're broadening this to the whole field of neural engineering, which is broad. So I mentioned BMI, and on that there was one picture of somebody using EEG to try and control a device. EEG, unfortunately, is very diffuse and very slow. They've had some success in doing word recognition for people who can't speak, but it has not close to the bandwidth we need and data transfer we need to control an arm. It's also very cumbersome to put on the electrode hat all the time. You know, the direct cortical recordings get more data, and they're very excited, but of course they're very invasive. And unfortunately, we've not figured out how to make the electrodes last more than 6 months to 2 years. The nerve cells around the electrodes fibrose and become useless. In terms of stimulating muscles and FES, that's a whole different game. I oftentimes will get patients with brachial plexopathy where their nerves are damaged in the neck and they want me to come help them, but my technique is limited to having a healthy nerve, a healthy data channel, and a healthy muscle, a healthy amplifier. So if I don't have a data channel and an amplifier, I can't help.
Thank you very much.
I had a quick question about the signal processing algorithms. It seemed like you were decoding one class at a time from the videos. Is that true? And is that a hard problem to try to do something like elbow flexion and hand close at the same time?
Yeah, so when we do the pattern recognition, we've tested a gazillion algorithms, the LDA, SMV, fuzzy logic, neural nets, and I'm sure a real engineer could list even more. And they all turn out about the same if you do it offline. They all plateau at about 95%. We find a bit more difference when we do it online, real time. They don't look as good. They don't do as well, although the accuracy does not seem to be the only factor because the correlation is by no means perfect. There is room to grow new and better algorithms, and especially in the leg where you have a set time history and it's not a static problem, it's a quasi-static problem, and you can learn from where you've been. My colleagues are starting to use Bayesian statistics, and I can barely spell Bayesian, far less, do anything with them.
Thank you.
Todd, could I ask one question? And that is, could you say just a little bit about mounting to the body? Because you've talked about the importance of lightweight, but I presume that there's sort of a trade-off with the weight and then the effectiveness of the mounting to the body.
Thanks for that question, because that is probably the biggest challenge and problem in prosthetics. The way you wear a prosthesis now is that you have a plastic socket that goes over your residual limb, a cup. And I'm going to use the leg because it's a better example than above knee amputee. So you got this big cup, and there's some muscle in there. We all got our fair share of fat, believe me. And an amputee's muscles atrophy and they get even more fat. So as you put this cup on, you're trying to walk with essentially a stick, your long bone, your femur, in a bowl of Jell-O, that's hugely compliant, and move this relatively heavy mechanical device. So I think sockets just plain suck. We need to be able to do better. There's been a lot of research over the year. We've improved materials, we've improved suspension systems. The designs are getting a bit better on how we can lock into certain parts of the body. But in the long run, what I truly want to see is direct skeletal attachment. The idea of having a metal rod go into the bone, long bone of that transfemoral amputee, and stick out through the skin so I clamp on to that metal rod and my prosthesis is directly attached to the long bone system. There is a group in, probably the leading group in the world is Richard Brannemark in Gothenburg, Sweden. He's developed a system that's really quite clever and has it on maybe 200 patients around the world. He does not have it FDA approved in the United States, although he's apparently been trying for a long time. It does have a challenge in that, and they all have a challenge in that you got a metal rod sticking out of your leg, you're going to have a chronic wound, okay? Because there is no way to make skin grow into titanium or any other metal. So you have to manage that. And the way Richard does it is by having the end of his bone be solid, and then he scars the skin right down on the bone, which is kind of a stress shield. So if you pull on the tissues, it doesn't stress the implant. The problem is he's only 2 millimeters away from osteomyelitis. So other people are working on this problem, and I would consider it the holy grail of prosthetics if we could figure out how to attach directly to bone. And the patients I've seen, they love it, and it's really exciting.
Thank you. And with that, I think we're essentially out of time, so let's thank Todd one more time.
Thank you.